Okay, our section of notes today is about freefall. Freefall is a special type of motion, and it's a motion of an object that's falling freely and landing and hitting the earth. The reason why we have freefall is because of gravity. Gravity is pulling on an object. So the definition of freefall is that it's motion due to the influence of gravity only. Now, on the surface of our planet, everything falls through the atmosphere, and so the atmosphere has some type of resistance, friction, fluid friction, if you will, air resistance. And so in order for free fall to technically be occurring, there should be no air resistance, no friction can be present. So, we really don't have free fall on Earth, but we can still talk about it as if we do. So gravity pulls and increases the speed at a rate of 9.8 meters per second for every second. Now, this is the acceleration due to gravity. It's in physics what we call a constant. It's a number that does not change. It doesn't matter if I throw Isaac out the window, an elephant out the window, a bowling ball out the window, a hamster out the window. Although, quite honestly, I would never throw a living creature like an elephant or a hamster out the window. Let's be serious. They're all going to fall at the same rate. That rate is going to be, they start at 0 and they increase in speed by 9.8 meters per second for every second that they fall. So it's a number that you really should be familiar with. Constants, we tend to want to memorize. The speed of light is a constant, and this acceleration due to gravity is a constant. So let's take a look at this. So let's say that I have a ball in my hand, and I hold it out at arm's length, and then I drop it. As I'm holding the ball, before it starts to fall, at 0 seconds in its time that it's been falling, it's going 0 meters per second. After the first second, it's going now, because of the acceleration due to gravity, 9.8 meters per second. Now we're rounding this up to 10 just to make it easy. So 10, after 2 seconds, it's going 20 meters per second. After 3, it's going 30, then 40, then 50, until it hits the ground. Because of gravity, Earth creates free fall motion, and it's the same for all objects on Earth. They're all going to start at 0. They're all going to be dropping at the same time frame. Okay? Now remember, free fall is without air resistance. So you take away the air resistance and all things fall at the same rate. As we were saying, free fall on Earth doesn't really exist. All motion on Earth is under the influence of the atmosphere and air resistance. But we do make some exceptions. There are some exceptions. For some very small objects with smooth shapes, air resistance is so negligible that we don't even count it. Something like a small caliber bullet coming out of a gun, and then it comes out of the gun and then it free falls to the earth. It's so small and it's moving so quickly. Air resistance is negligible, so you could really say that it's free falling. And the other time is that we're going to choose to ignore the fact that there is technically no free fall for our problems here in class. So if I give you a free fall problem, you can't answer it by saying, well, technically it's not happening because of air resistance. You have to pretend like it's happening. So the acceleration due to gravity on Earth, as we said, A, is 9.8 meters per second per second. Each second the object falls, it'll gain 9.8 meters per second. This is why you're not allowed to throw things off the Empire State Building, right? Because the Empire State Building is so tall, it takes quite a bit of time for us on something to reach the ground, and theoretically it's going to gain 9.8 meters per second for every second that it falls, so it's going to be moving pretty darn fast, bullet fast, let's say, by the time it hits the ground. Okay, so if I want to figure out how fast something is going after it's fallen for a certain amount of time, I can use an equation. Velocity equals the acceleration times the time. Okay, so how fast is it going? Let's say I did throw it. Let's say the class goes to the Empire State Building for a field trip, and I decide I'm going to throw Michael off the top of the Empire State Building. I can't take it anymore. I'm just going to push him off. As he's falling, he's like, geez, I'm going pretty darn fast. I wonder how fast I'm going. He could pull out his handy scientific calculator. He could figure out I'm falling at 9.8 meters per second. That's a constant I have memorized thanks to Miss Mateer. And I've been falling for about 10 seconds. Holy cow, I'm going 980 meters per second. Okay? Now, this idea of free-falling gravity works, and gravity accelerating an object works of opposing gravity as well. If I throw the ball up into the air, it slows down, eventually reaches a peak, stops, and then begins to fall due to gravity. So as it's going up into the air, it's going to lose 9.8 meters per second for every second that it's moving upward till it stops at 0, and then it will fall back down. So if I throw up this ball up into the air, it's going 30 meters per second. After another second, it's 20, then 10, then it stops at 0, and then it'll begin to free fall back to Earth. Right? Returning at 0, 10, 20, and then 30. Remember, we're just rounding off 9.8 to 10 just to make it easy. So as Michael's falling from the Empire State Building, he's like, wow, I wonder how far I've got to go before my brains are going to squash onto the sidewalk. Oh, I know. I can calculate that using the equation we were given in Mrs. Mateer's class. The acceleration due to gravity times the time squared times 1/2. Now remember, order of operations, you should square your time first, then 9.8 meters per second squared, and then multiply that by 0.5. Now that brings us to something that we call terminal velocity. It's it's a speed that objects, as they fall, it's a myth actually that things will be going bullet fast when they hit the Earth from the Empire State Building. And the reason for that has to do with this idea of terminal velocity. Because there is air resistance on the Earth, you're going to be falling, and your velocity is going to increase. Eventually, you're going to get to a point where the air resistance is going to exactly balance out the pull of the force due to gravity. When we have balanced forces, we no longer accelerate, right? So we will quit accelerating and we'll just start falling at a constant speed. Once you reach that constant speed, due to that opposing force between gravity and air resistance, you're now falling at terminal velocity. For an average-sized person like Michael, when we threw him off that would be 200 kilometers per hour. Still pretty darn fast, but you're not going to reach speeds of like 900 and 9,000 kilometers per hour or something like that. Okay, so we're going to further take a look at this concept of free-falling gravity by working through some of these equations to find the distance and the velocity that we're going and the time that it takes for free-falling objects to fall in class when we see each other next.